We're going to start our first talk in the gallery track. His name is Andrew Mcveigh. He's a software developer at uSwitch from London, and he's going to talk about leveraging clojure.spec for API documentation. So let's all give him a warm round of applause for the first talk of the day. Thank you, Andrew.
Can you hear me? Okay. Repeating stuff hurts, but we always have to repeat things. We're always having to repeat ourselves in slightly different ways. And at uSwitch, we tend to split large systems into smaller, more specialized services because it gives us a lot of flexibility. But with all these different services, all these different APIs, this tends to lead to lots of different specialized data structures. And these data structures can contain lots of the same or at least very similar information. It can be different views or different versions of the same data. And it becomes a lot of work to maintain compatibility between these different versions. Now, clojure.spec is a tool that can help prevent you making mistakes when you have to repeat yourself. You can use it to describe in detail all your different data structures and your functions. But if you're going to spend all that time and effort deeply describing your data and all your functions, you're going to want a lot of leverage for that. And, well, I think spec does give you a lot of leverage, but we wouldn't want to have to repeat all that effort. So why would you use clojure.spec? It sits in a similar space to prismatic schema, and it's mainly concerned with data validation, generative testing. It is designed to enable richer documentation for functions, macros, and your data. And it's also turning out to be really awesome for parsing Clojure code and for parsing Clojure data. So this is an example of a Clojure spec. It's got a fuel, which could be electricity or gas, and a variant, which is the type of electricity meter, and that's just a string. And the energy meter as a whole is a map, and it has two keys, fuel and variant. And you'd use clojure.spec if you want to make sure that what you have is an energy meter, and say not a list of dairy products. But what is a spec? A spec is a Clojure value, and it could be a predicate function from Clojure core, or it could actually be any arbitrary function you write. It can be a set of values. And clojure.spec has a number of other types that can help you define the shape and the type of your data. So that we can combine and compose specs, we name them, and we put them in a global registry with def. The specs are named with a namespace keyword. But at the bottom of it all, a spec is something that implements the spec protocol. Clojure.spec has a number of higher-level functions that act on these protocol functions. So conform says, does the data you gave me look like this spec? And if it does, give me the conform data back. Conform data is like this bit. I can't reach that one, sorry. That is the data structure you gave plus any destructuring done with an OR spec or certain types of regular expression specs. Each spec knows the rules of its own conformity, and that means to also check whether the child specs also conform. Unform simply removes any destructuring done by conform, so it will give you back the original data structure you passed in. Explain will say, given a spec and some invalid data that doesn't conform to the spec, how did it fail in detail? Gen simply returns a generator for a spec, so you can use that to generate random or semi-random data. And with gen allows you to provide a generator for that spec if you need a better quality generator or a faster generator or something that will give you real-looking data rather than random data. And describe will give you back the original spec that you used to declare. So the clojure code form that you used to declare the spec. And describe is designed to return a spec that you can send over the wire. Now, one criticism I've heard of spec is that it's opaque, that the data of the spec themselves is inaccessible. But nothing in a Lisp is really opaque. It might take a little bit more effort to get the data, but we have the clojure reader or analyzer at our disposal, and even if we had to drop down to the code as text, it's still just data. But in this case, we don't have to go that far, because form will pass us back the clojure data that was used to describe that spec. And once we have that form, we can do a bit of analysis on it, turn it into perhaps a more easy-to-use tree. We expand these specs, and as we come across a spec, we can expand those into a tree, and then this tree becomes as easy to interpret or to manipulate as any other clojure data structure. Oops, excuse me. But what's the point? Why would you want to do this? I guess the reason is sometimes there are going to be things that you want to do with spec that it doesn't support. And the first thing that we wanted to do was to render specs themselves into a different format. We'd had kind of a decent experience with Swagger for documenting our APIs. It's not perfect, but nothing is. Swagger needs a JSON description of your API. And the format it wants that description in is json-schema. So we wanted to render something that looks like that into something that looks like that. And at the time we were doing this, there was clojure-spec was too new for existing libraries that render Swagger in Clojure to have any solution for this. And I think that's still the case. I'm not sure. But given that we've translated our Clojure specs into an abstract syntax tree of sorts, how hard can it be to convert this tree into one that looks like JSON-schema? And it's pretty straightforward to transform a tree into another in Clojure. That's kind of what all those data transformation functions are for. You can simply walk the tree, substituting specs for JSON-schema definitions. And if we change the shape a little bit, collections become arrays, maps become objects. We can then spit out that tree with any JSON serialization library. But what are we missing? Like, what's spec not got? And although spec is a more powerful data specification language, it's not necessarily concerned with everything that JSON-schema is, at least not yet. So this is a diagram of an MPAN, or a meter point administration number. This is like a unique identifier for a UK electricity meter. Now, before I started working at uSwitch in energy switching, I had no idea what this was. I didn't know that it had two different components, the top line and the bottom line. I didn't know that each segment of this MPAN means different things. I didn't know what they meant. And to be fair, you all don't need to know that, and I suppose most of the time, neither do I. But sometimes, as developers, we do need to know what our data means. And isn't it nice when an API will tell you that? It will tell you what the data means rather than just what shape it is and what type it is. But how can we do that with clojure-spec? I suppose, like, at the moment, we can't. But clojure-spec is pretty flexible. It's flexible enough that we can extend it so that we can do what we want. Clojure-spec is a domain-specific language, and Lisps make language extension really simple. Clojure-spec is defined in terms of a protocol, which makes extending that in Clojure even more simple. And I know right now, at the moment, there is an open question about whether spec will get metadata or doc strings, just like regular Clojure. But we don't need to wait. Spec is flexible. We can do this ourselves. So this is an example of an extension. It's a very simple thing. I've called it a doc-spec. It doesn't really do anything. It's a spec that passes all responsibility of conforming and unforming to another spec. But what it does is it hides a doc string in a clojure. And you can get that doc string out with the protocol function docs. Now, it's a macro because here we need to capture the form that we pass in so that clojure.spec can then pull that out again with the describe function. But you're free to override any of these protocol functions if you want to change the behavior of, say, conform or unform. This might be how you would use it. You call it with a doc string, and you pass it the spec a string. And all of the more complex clojure.spec specs are defined in this way. They're defined as a macro over a reified protocol. Now, at uSwitch, we don't just write things in Clojure. We have a number of other systems that don't speak Clojure. We have the majority of our website is written in Ruby, and a growing number of utilities and tooling written in Go. And these obviously can't use clojure.spec directly. Is that right? Where was I? All right. So in these programs, we might want feedback about the data structure that we were building up, that it's correct. And we want that without trying to hit an API. So we'd like that without having to repeat all this effort. But if we add enough vocabulary so that we can generate rich JSON-schema documents, we can maybe spit them out to S3 or publish them to a schema registry. And then we can consume them with, say, a Ruby program and use a JSON-schema validation library to check that the data is the right shape and the right type. And although JSON-schema is not quite as expressive as clojure.spec, the interface between our Clojure and Ruby apps is JSON, so it's about good enough. So that's our clients taken care of. How can we protect our APIs? One way we can do that is to spec the parts of a HTTP request that we care about. And that's mainly going to be the request parameters. And our responses, we're probably making some sort of RESTful API. Our responses are likely to contain our domain models, more or less, maybe a different version. And they're going to be wrapped in a ring-like response, maybe a hypermedia envelope. And we can spec that. And the response is going to be one or more types of response. And they're each going to have a different status code. And we can represent that with an OR spec. And we have this kind of pattern, especially in Ring, that a request handler is a function that takes as its input a request and returns a response. And clojure.spec's fspec here is the specification of a general request handler. Its argument is a request, and its return value is a response. And we can use these specs to enforce, like, at the boundary of our program, that the shape and type of the data that comes in and out of our application is correct. We can either manually assert these things, or we could maybe hand that off to middleware, but we can also instrument our request handlers and data producers. We can use test.check to drive hundreds of tests against this to kind of throw lots of generated data at our API and have generated data come back out, and to check that the shape and the type of the data is still correct. Generative testing of APIs is really that simple. But is that enough value yet? Is that enough for all that time and effort that we spent speccing every inch of our data structures and our functions? Is this enough value to justify all that work? I think, like, maybe it is. It probably is. But we can do more things with spec. We can use specs to derive a data transformation function between two specs. Oh, that's cut off. Oops. So these abstract syntax trees that we've built, You can think of them in another light as a detailed mapping of the structure of your data. And each tree is kind of like a roadmap or a signpost to each different value. And if we had two different trees where the leaves are more or less the same, or maybe there are some missing, but the structure might be different. And we can work out how to use this mapping to convert a simple data structure into a slightly different shape. For example, like a database row, a flat structure like a database row into a nested map. And we've used this at uSwitch. We can convert a large flat structure into many different views, depending on what the client wants to see. But this kind of works only for simple structures. And to do this, the data or the leaves must be uniquely identifiable somehow. So, for example, a database row, the uniqueness is in the name. We can easily just pull those out into a hash map shape and use it to build up any structure. But sometimes the uniqueness is not just in the name, or usually it's not just in the name, it's also in the structure of the data itself. The uniqueness can be in the path you take to get to the values. And sometimes it's not even in the name or the path, it's in the data itself, it's in the type of the data. So what do we do when the data structures are even more complex? So lots of us, at least at uSwitch we are working with lots of different complex data structures. And over time, things tend to evolve, and due to lack of constraints, ensuring that they stay small and neat, things can turn a bit monstrous. They have lots of interesting features, like optimization for HTML rendering, or there are many different implementations of some types, some pretty bad and some terrible. And this is where using just name and structure to define whether values are unique or not, it starts to break down. But we, as humans, can tell the difference. We can see patterns in the data. So this is something we'd have to help our program with. We need to increase the vocabulary a little bit again, so we can instruct our transformation function which fork in the road to take when it comes across one. And to do this, we're going to categorize them. And this function categorizes a spec. It tells us how values below a tariff, or all the values in a tree of values that represents a tariff, how they are different from each other. Tariffs are categorized by both fuel and payment type, and the functions next to them there, called on the data, will tell you what the type is. And every value beneath this point, here and there, should be categorized by the values there. And if we were to flatten each subtree below that point of all the values, all the values below that point into one set, if we did this to all the different subtrees, we would want the union of all those sets to be disjoint, so that we haven't lost any of that information that we would need to build it back up. And when we do build it back up, or if we try to build it back up, then this categorization is less about the actual category of value that's kind of already been done. The set is already disjoint. It's more about a branching point where the set needs to be split by which categories. And we'd like to do this with the same vocabulary, if we can, so that if it's possible, if two data structures were isomorphic, we could do a transformation in both directions. But we also needed a little bit more. We needed to add more to the vocabulary to tell the transformation function specifically what type of data goes down this branch. And if we can express this, we can transform lots of different, even more types of data structure. And here this kind of represents that for the key electricity, only keys with category fuel, where the type was electricity, can go down that branch. And for gas, the same, gas. And using just this simple vocabulary extension, we can transform lots more complex API responses between different views and formats. We can even transform quite large, complex data structures. Up to 1 megabyte is kind of the largest data structures that we've been able to transform with this. We've been able to slim down these data structures into kind of much simpler, more specific versions so that the documents that we're talking about are much smaller. We've even tried out kind of crazy stuff like posting a brand new spec to an API to get a response in that spec. And although that's probably a terrible idea, you don't want to be evaluating code that you post to an API, it does actually work. We can use this same kind of technique to extract data, because really an extraction is just a type of transformation where we throw away most of the data. And we can work out what kind of data functions need from its fspec. So like this function accepts VAT and rates, and its fspec reflects that. And we can maybe use a different calling convention, like here xApply would take a spec of a function and a giant data structure, and it could extract the data from the data structure and then pass it to the function. So we've managed to extract most of these ideas into a library. It's called Speculate. There's still a lot of work to do. The transformation algorithm it's not really efficient. It's experimental. It's a bit more than a proof of concept, and it's likely to change, but it works for us. So at uSwitch, I'm not sure we'll be in a place where we stop creating specialized services and data structures, but we are in a place where our data structures need to change because of network constraints and changing business requirements. But now we're in a place where dealing with all this is a lot simpler. It's less painful. It doesn't hurt as much. We just have to write the specs, at least in our Clojure code. And I think all this effort of writing specs is worth it because you can use those specs to reduce all that repetition. Thanks.
Thank you very much, Andrew.
Thank you.
If there are any questions, please raise your hands. I will bring you the microphone such that we have your question on the video recording. So, no questions left? Right. Everything answered. Thank you very much, Andrew.
So. Thank you.